Hello, this is the third part of the chapter 6.2, and we'll talk about the orthonormal set. So what is the orthonormal set? Okay, the name probably will tell you already by itself. It's the set of orthogonal net vectors which has a length of 1, or their unit vectors. And the convenient thing about these vectors, if we have a subspace spanned by orthonormal set, it forms a basis, and not just the basis, but the orthonormal basis. And you all probably familiar with this kind of basis. For example, the basis vector E1, E2, and so on for the Rn are orthonormal basis. For example, for planar system R2, our two vectors 1, 0, and 0, 1 is form orthonormal basis. They are perpendicular to each other, and each vector has a length is equal 1. But we're not really limited by our standard vectors. Any system of orthogonal vectors, unit length 1, should give us an orthonormal basis. For example, let's look at these three vectors, v1, v2, and v3. They supposedly form an orthonormal basis. Let's just actually check if they indeed form such basis. And that's really pretty straightforward problem, because first we need to show that they are orthogonal, second, that they actually has a length is equal 1. So let's start with the orthogonal systems. How do we know that v1, v2, and v3 is orthogonal to each other? Of course, we will use the dot product property. We try to dot product of every single pair of out of these vectors, which only 3 pairs, and see if each one of them is equal 0. Okay, let's calculate v1 dot v2, it's equal 0, then dot product v1 and v3, still 0, and finally v2 and v3, still equal 0. So our answer is convincingly yes, this vectors seems to be orthogonal. Okay, are those unit vectors? Again, or the normalized vectors, let's just calculate their length. And that's just the dot product of vectors, v1, v2, or v3 on itself. Okay, let's look at the length of the first vector. Seems to be equal 1. The length of the second vector, 1. Length of the third vector, still equal 1. So again, our answer to our question is yes, it is a normalized. It has all of 3 of them are unit vectors. So that's enough to show that 3 vectors form orthonormal basis, orthogonal and normal. We are set to go. So what's so special about them? Oh, the matrix which form by orthonormal basis has a very, very interesting properties. So if this matrix usually denotes by U, and it's just the columns of our orthonormal basis vectors. First, if we take this matrix U and multiply by its transposed, we should get an identity matrix. And that's very interesting, unique, and highly unusual in the matrix world. But it's not the only interesting property. It also has a couple other properties. For example, if we multiply our orthonormal matrix U by the vector x, then we should get the same length of the vector as the vector x itself. Also, if we multiply our orthonormal matrix U by 2 different vectors, x and y, and calculate the dot products, again, it should have exactly the same dot product as the x times dot product with U itself. And finally, if we have a dot product of matrix U applied to vector x and matrix U applied to the vector y, and this dot product is equal 0, we can convincingly conclude that its dot product of x and y is 0. So, and again, all of this proof of these properties you can find in the books. I'm not going to talk about this here, but please go and go through the derivation. It's really interesting one. Here though, let's just try to verify one of the properties. Let's take vector u, which is supposedly an orthonormal matrix, and let's take a vector x of 2 components. And let's try to verify the first property, that the matrix u times our vector x has a vector length the same as a vector x itself. Okay, let's start from our matrix u. You probably should not be convinced that indeed it has orthonormal properties. So let's just calculate. Let's take our matrix u, transpose it, and multiply by matrix u itself, and see what kind of matrix we will get at the end. And you can carry out the calculation and confirm that indeed we have an identity matrix. So okay, the theorem 6 seems to be holding. Let's try to calculate the product of our matrix u by vector x. And okay, so that's our vector. So we are looking for the property A, which tells us that the length of vector u times x should be the same of the length of vector x. Let's calculate our lengths. So let's calculate the length of ux, which is square root of 11. Now let's go back to our original vector x and calculate its length, also square root of 11. So it does seem that our matrix u is orthonormal, and it's also our first property is holds. Okay, now I would like you to go to the end of chapter 4.6.2 and try several exercises on orthonormal basis.